Morning, everybody. This is Mike Human, and this is the start of our G2M Research Multi-Vendor webinar on composable infrastructure, what it is and why it's important. The sponsors of our webinar today are Western Digital, Liquid, and Gig.io. We'll give everybody a minute or two to join in, and then I'll go through the ground rules and give a brief intro before we jump into the webinar. All right, so let me kind of walk through the ground rules and the agenda. So we will have a presentation from each of the three sponsors. Presentation will be about 10 minutes, 7 to 10 minutes. Then we'll go through three key panel questions. During those panel questions, we'll also have audience survey questions, and then we'll wrap it up with an audience Q&A. For questions and answers, please use the Q&A window on Zoom to submit your questions, and then we'll take them at the end and go through all of them at that point. The other thing is we will make the link to both this recording and to the slides available to everybody. That should get sent out to you sometime on Thursday, so be looking for that. And with that, let's go ahead and get started. So our panelists are Dave Montgomery. Dave is Director of Data Center Systems from Western Digital. We also have Sumit Puri. Sumit is the President and CEO of Liquid. And finally, Alan Benjamin, who's President and CEO of Gig.io. And then I'm Mike Human, Managing Partner at G2M Research. So what is composable infrastructure? So really, composable infrastructure is kind of the far end of, if you think about server or data center disaggregation. The idea is to take everything apart into their component pieces and be able to, through software, compose configurations that you want. You know, some of the types of resources you might share could be GPUs, could be FPGA or ASIC-based accelerator cards. It could be storage things such as SSDs or Optane memory or complete arrays. It could be anything in between there. And the idea is to be able to move these things around and connect them or disconnect them to servers or workstations as needed. Generally speaking, some sort of fabric is utilized to connect all these components together with the servers that are going to actually, could somebody out there mute? Sounds like we got some feedback. Thank you. That is used to connect these resources to compute nodes. Those can be anything from PCI Express to InfiniBand to Ethernet or anything in between. And then the last piece of it, the most important piece, is there is typically a management system or some sort of management software that's utilized to manage these connections and manage the resource, providing those resources off to other people. Is it a new concept is a question I hear a lot. And having worked at a company that did something called I/O virtualization 10 years ago, it's not new. It's certainly better than it was back then. Composable infrastructure has been around for a long time. I/O virtualization was one example of this. It really focused on sharing of I/O resources, which were at that day very expensive. Things like Ethernet NIC, fiber channel HBAs, InfiniBand HCAs. Some vendors, including the one I work for, were able to share GPUs at that point in time, but only the entire GPU, and it was generally fairly static. Most of the people doing I/O virtualization back then did PCI Express or InfiniBand as their fabric. So some of the key elements that our panelists will talk about are the things that have been added to composable infrastructure since then. Ability to add and delete resources from the resource pool, to be able to do so without reboots of the servers or workstations, and then dynamic provisioning of resources. All the sorts of things we've gotten used to being able to do today at the server level, composable infrastructure can handle as well. One of the questions I also get is, why would somebody want to use composable infrastructure? I mean, there's all these different sort of architectures out there, including hyper-converged, standard server storage infrastructures, and composable. And if you think about composable, the place where it generally tends to have the most value is places where you've got a lot of expensive resources that are intermittently used by a user. So if you imagine, say, video post-production, right? I might need a bunch of GPUs to do some production work, but I may only need it for 3 or 4 hours of a given week. I may also need a bunch of storage that has all the raw footage, but then I want to be able to pass that storage to the next person that's in the workflow. So composable infrastructure gives you all those capabilities. The example we have here says, if you think about a pre-production situation where you've got a GPU, a bunch of GPUs, some expensive Optane storage, if you were to put all this in a workstation, it costs you about $6,200 a workstation. If you got a big team of, say, 100 people, that's $620,000. If you're able to share it, assuming people on average use each resource about 10% of the time, you could cut that cost down to about $62,000. And then you got to throw the composable infrastructure cost in on that, but obviously there's a lot of room for you to save some money going that way. And with that, let me pass it over to Dave. Dave is from Western Digital. Dave, I'm going to give you control now.
All right. Thank you, Mike.
All right.
Good morning, everyone. Good evening, depending on what time zone you're in. I'm Dave Montgomery. I'm with Western Digital's Data Center Systems business unit. We make storage platforms. But really, I'm not here to talk in any detail about our portfolio. I want to sort of extend on what Mike said, and we share his vision of a composable infrastructure. To state the obvious, Western Digital makes storage, makes a lot of storage, makes hundreds of thousands of disk drives a day, SSDs, et cetera. But we recognize it's only one element in a IT environment or in an application environment. So there's a lot of resources, and as Mike pointed out in the previous slide, there's a lot of expensive resources. And the intent is, or the desire is, to get as much out of those as you can, since they're expensive investments. You've got compute and different flavors of compute, whether it's CPUs, FPGAs, or GPUs. You've got networking even, virtual LANs, and eventually you'll have a memory fabric connecting a high-speed, low-latency DRAM fabric. And then you've got the actual memory itself, being able to allocate memory on the fly, and even storage class memory, even persistent, non-volatile memory. So you have an enormous pool of resources, enormous expensive pool of resources that you want to get as much utility out of as possible. So the evolution of this is sort of aligned with virtual machines and virtual I/O, in that you want to be able to share these things simply because they're expensive and they're frequently needed, but it's too expensive to give an entire resource bucket, so to speak, to every user. You just can't afford it. So what's happening in the world is whether you call it a virtualized system or a composite system, it's essentially an extension of the VM, virtual machine concept, but at a much more granular level. What the vision is you want to be able to build a virtual system with certain ratios of CPU, disk, flash, DRAM, I/O bandwidth, and once you build that up dynamically, then you run your workload on it and you spin up other composites. And so what you have is essentially analogous to a bunch of virtual machines, a bunch of VMs running, but these are much more granular and composable on the fly. So again, Western Digital is a storage company, but we recognize particularly flash storage as an expensive resource, and the more you can share it, the better that return is on that investment. So how does this differ from hyper-converged? Hyper-converged is really good if you have a fairly narrow range of workloads. And you can utilize all the components in each of your hyper-converged servers effectively. However, if you have a divergent set of workloads, for example, a flash-intensive workload, let's say, you're utilizing well all the flash and possibly all the CPUs in each of your hyper-converged appliances, but your disk, maybe your memory is not getting utilized, it's underutilized, which really means you're paying for it, but you're not using it. So while hyper-converged will be tremendously useful in lots of environments, particularly where there's relative uniformity in workloads, there are many scenarios it just breaks down, and you end up having lots of unused resources under this sheet metal of a specific server. Conceptually, a composable infrastructure is really fairly simple. On the left, you see your classic hardware server, right? You got drives, fans, processors, memory, networking cards, GPUs maybe. And what you want to do is granularize, if that's a word, these resources. So essentially, you have the same performance and the same capacities of whether it's processing or memory or disk or flash, but they're all virtualized. And as difficult as it was in the mid-late 90s to think of a virtual machine, we're well on our way towards virtualizing all of the components you see down there on the bottom. And a key element of this is your orchestration software. So software that can identify and reallocate these resources. So in actuality, what it's going to look like, the first sort of incarnation of this composable infrastructure would be NVMe attached devices. Everything's virtualized. They're all peers. The CPU doesn't own the DRAM or the GPU or the flash or the disk. They communicate with each other and allocate portions of themselves, if not all of themselves. But it's a peer network among components that you can programmatically configure. This is kind of a good theory, but how would this work in the real world? So let's take the components you see below, right? Standard workload components. So our first workload needs a GPU and it needs a CPU. It doesn't need any FPGA and doesn't need any disk either. So it just needs some flash and a lot of processing. Maybe this is an analytics workload, who knows? But those are the share of resources it needs to run its job. The next one, it's a little different. It needs a lot of memory, a lot of DRAM, you see. And it needs disk and flash. So it needs both some capacity storage and some high-performance storage. It may need an FPGA to do some unique processing on the data. And then finally, we have a workload here, which is sort of a classic workload, let's say, a lot of disk, tiny bit of memory, and a core. This could be a backup, it could be an archive, some workload that is not performance sensitive, but yet needs a lot of disk capacity, a lot of storage. And then finally, we have let's say a unique workload. It actually doesn't need anything but an FPGA and a whole bunch of flash and DRAM. So this could be a transaction processing, it could be a high-frequency trading, it could be something that, while it's running, just needs those resources, and then it can reallocate them when it's done. So this approach will allow you to get lots of bang for your buck, so to speak, big return on your investment, because in any given moment, your resources are utilized as optimally as they can be. Now, Western Digital makes a product today in the flash storage business, as you'd expect, for disaggregated composable flash storage. It's the OpenFlex F3000. It's got 10 devices in it that are all composable, attached via Ethernet, NVMe over Fabric, and extremely high performance. Think of millions of IOPS per device. If it's a sequential workload, gigabytes per second in terms of bandwidth. But more importantly, it's incredibly low latency. It's like 30 microsecond caliber latency for a shared storage device. So from a utilization point of view, you now have a shareable storage resource with the latency of a DAS, a direct attached storage. Coming from us soon, over the next few quarters, we will have disk-attached devices. And to state the obvious, no one needs the performance that NVMe over Fabric can offer with a disk, but you do want the capacity to be able to be allocated and reallocated on command. So the same wire can control your disk as well as your flash. And then finally, next year, we'll be introducing some compute nodes. Again, hardware only, we're not a software vendor, but these are compute resources that you can share, as I showed in the previous diagram, for your composable workloads that you need to support. And a big advancement, we're going to announce this next week at Flash Memory Summit. We have constructed a lab, a partner lab. It's based in Colorado Springs, but let's be honest, you can remote into it from anywhere. The goal here is to establish the ecosystem, to give an environment for multi-vendor testing, so vendors and partners can come in, test their devices, see how they work, debug them, in interoperability issues. And as I said, all the devices are peers, so there's no hierarchy in the management of any of these components. And just a plug for the University of New Hampshire, if anybody on the call has spent any time in the standards world for, let's say, Ethernet or NVMe, University of New Hampshire's IOL lab has spent many years in this space, certifying compliance of various protocol stacks and standards. So we're doing this in very, very tight collaboration with them. And that's really it. I'll turn it back over to Mike, and I look forward to your questions during the Q&A period. Let me give you control.
Thank you very much. That was great stuff, Dave. All right, looks like I've got control. Okay, next is Liquid, and it's not Maria, sorry, it's Sumit. Sumit is going to be doing this one. So Sumit, I will let you have control. Go ahead and take over.
Yeah, thank you guys. Appreciate the opportunity to share our story with you guys. Let me make sure the slides are working here. One of the main problems that we believe composability is addressing is around the poor utilization rates of this very expensive hardware that we are all deploying inside the data center. The way that we're viewing it is there's a fundamental transformation. Sorry, the slides are going wrong here. There's a fundamental transformation going on inside the data center. We're moving from what we referred to as statically defined infrastructure to fully dynamically defined infrastructure. And today the big buzzword is things like hyper-convergence as a way to raise the utilization rate of that hardware deployed inside the data center. If we listen to what industry analysts like Gartner and some of these guys are talking about, the next chapter or the next evolution of how we build the data center is around disaggregation and composability. First, disaggregate those data center resources and then compose your servers based upon pools of disaggregated elements. So what we mean by composable is a new way of building servers inside the data center. In our world, we don't define a server by plugging devices into the socket of the motherboard. With composability, it's about taking pools or trays of resources, trays of storage, trays of compute, trays of GPUs, FPGAs, Optane memory, networking cards, whatever physical resources you're using inside your data center. Instead of plugging those into a motherboard, we plug them into a fabric switch. And then we come in with software and we dynamically orchestrate or compose at the bare metal. Grab me this CPU from this tray. Grab me those 8 SSDs, those 12 GPUs, and those 2 FPGAs, and build me a server. Just like you were putting stuff into the motherboard, except you're defining it in software. And on the other side, you're getting delivered physical infrastructure of any size, shape, or ratio that you want. Except that infrastructure is dynamic. When we need to add another GPU to our server, we don't send a guy with a cart to power the machine down. We just reprogram the fabric and dynamically add or remove resources depending on what the application layer is requiring. A couple of kind of use cases we like to talk about. First one, for example, is in the transportation space. If you think about what happens at 5 p.m., very different than what happens at 2 in the morning. And a lot of times, customers play this game of workload matching. Small workload, small server, and the world is great. Small workload, large server with 8 GPUs attached, we're throwing away a lot of physical resources. So in our world, we say, let's take a new approach at this. Let's study the workload as it comes in, dynamically spin up small, medium, large, extra large, however big of a machine we require. As soon as the work is done, free the resources back into the general pool and let somebody else have it, that very expensive resource. And this is how we think we change the fundamental utilization rate of the hardware that you're putting into the data center. And for a lot of our customers, it's not even a question of is dynamic better or is static better. We know dynamic infrastructure is better. For our customers, their question is Am I going to go AWS? Am I going to go public cloud? Or am I going to keep these workloads on-prem? And our value proposition, the value proposition of composability, value proposition of bare metal composability, is the ability to give all of that flexibility, all of that agility that the customers get from public cloud, where we can save them a ton of money by deploying those resources on-prem or at a colo, basically taking the infrastructure and allowing the customer to own it. And we're seeing a trend. We're seeing the pendulum swing. The dream has always been public cloud is going to suck up everything. The reality of it, it's going to be a bimodal world. Some amount of my infrastructure is going to live in public cloud. Some amount of my infrastructure I'm going to be responsible for. The infrastructure that I'm responsible for, we think can benefit from agility, flexibility, and composable type environments. AI is a big term. Everyone's talking about it, right? It's kind of this like mysterious thing. Everyone knows they want to be a part of it. The market is huge, right? And it's touching all aspects of life. But what is AI? AI is not a event. AI is actually a workflow if we look at it, right? The first thing we're doing in our AI workflow is we're ingesting data. That's normally very networking heavy. Then we move on to things like tagging and cleaning and scrubbing. And there I'm normally using a lot of CPU horsepower. Then we move on to things like training. And here it's probably, NVIDIA V100 GPUs and multiples at a time. And then we move on to inference, which is another type of GPU, probably only a single one. And at the center of all of this AI work is data. And data has gravity. It's very difficult to move data around for the different phases of AI. So in our world, we believe composability is the right answer. Let's bring the compute to the data. Let's bring the GPUs to the data for the different phases of the AI workflow. So we're going off and we're developing composable solutions, specifically targeting areas like AI. This is probably an extremely easy one to understand. This is our media and entertainment deployment. We have a customer who uses these very expensive accelerators, 4 of them in a box. During the daytime, they compose those accelerators over to their AI engineers. When those guys go home at night, they recompose the fabric and give those same accelerators to their video rendering server. Basically, they've taken $50,000, $60,000 worth of hardware and doubled the utilization of that hardware by making it composable. We talk a lot about the benefits of dynamic infrastructure and all of the good related to being able to physically move resources around. There's a handful of other benefits that come with disaggregation. Number one is the independent scaling of resources. What's the fundamental problem with hyperconvergence is the fact that it's converged. As we are adding CPU, we're inherently adding networking, storage, and everything else. As I add storage, I'm paying for compute. With disaggregation, we can decouple those decisions. We can independently scale GPUs without paying for additional storage. The next benefit is extending the product lifecycle. Your customers have bought equipment, they've bought infrastructure, they've bought servers. And now what they're saying is, I need to augment those servers that I bought with NVMe capability. What do? One option is, buy additional servers that give you more NVMe capability. The other option is sell trays of resources and augment your existing infrastructure. The other benefit is decouple the purchasing decisions. Right now, when we buy compute, we're actually buying compute, storage, networking, GPU capability, all in one shot. With the benefit of disaggregation, I can buy my compute completely separate from my GPU requirement, completely separate from my storage requirement. Let's break apart that purchasing decision. Intel is at a different cadence than is Samsung on the SSD, as is Mellanox on the networking. Why do we do rip and replace? Why, when Intel comes out with a new processor, do we throw the old box away and move the data up to the new box? With disaggregation, we think we break that rip and replace cycle. The other benefit is the impossible configuration. I can't take a 1U pizza box and attach 48 SSDs to it. But with a composable environment, I can take a 1U pizza box, attach 48 SSDs and 16 GPUs. And if you're using the right fabric, that pizza box will never know that those resources are composed in. The other benefit is pay as you grow. Don't pay for everything up front. Buy the resources as you need them. As you need to add trays of storage, just add trays of storage in the future. Don't buy everything up ahead. And I think the last benefit is massive, right? This is around software licensing efficiency. In our world, all of our software lives on our Fabric switch. So when we compose a server for you, it is truly a bare metal server. Run whatever software you want on top of it. In a normal environment, how does things like VMware, Oracle, SAP, how do they work? We buy a box, that box has resources, we pay for our software license. When I need additional resources, I buy another box with another x86 processor on it, and I pay for additional software licenses just to get those additional resources. In a composable landscape, we don't do that. When our box runs out of storage to virtualize, we just compose in more storage and we don't pay for additional software license. So as efficient as we are for hardware utilization, we think we can be equally efficient for software licensing. I'm reaching the end of my time here, so I'll just kind of end it with where we see traction in our environment. Obviously, we talked a lot about AI workloads. These are AI, FPGA, GPU, accelerator type workloads. With composability, we can scale those resources out. We can share those resources, and we can accelerate those resources with things like peer-to-peer capability done at scale across the rack. We're targeting dynamic cloud, right? These are the 300 cloud service providers and large organizations who can't move their records to public cloud. We think private cloud, on-prem cloud, all of those can benefit from getting dynamic. We think HPC is the natural fit for this, especially when we're leveraging things like a PCIe-based fabric. If we talk about low latency and large amounts of connectivity, that's best done on things like PCIe. People get excited about low latency Ethernet and they say, I've achieved 1.5 microseconds of latency on my Ethernet interconnect. With PCIe, our latency is 150 nanoseconds. That's 10 times lower than what we can achieve on Ethernet. So HPC is a natural fit when we're composing, leveraging a PCIe fabric. And in our world, we support PCIe fabrics, we support Ethernet fabrics, we're a multi-fabric solution. It's which tool do you want to use for which job. And the last area for growth for us is really what we see as the next generation of data center build out. We don't think the next data centers are large boxes in Arizona and the desert. We actually think the next data centers are regional deployments close to the point of data ingest. And we think, that's a box underneath a tower, for example. And those things are limited by power, floor space, cooling. And if we can raise the utilization rates of the hardware by making it composable, maybe we can take a rack that's 20% utilized and get 40% utilization out of it. And if we're able to do that, then we think we're a natural fit for those 5G environments. And guys, I think that's my time. I will hand it back.
Thanks, Sumit. That was excellent. And with that, let's go to Alan. Alan, I'm going to pass you control right now.
Okay, thank you.
It should be yours.
Good morning to everyone. Okay, so let's step back for just a second and talk about why some of these changes are taking place. Both Dave and Sumit did a great job in talking about what that composable landscape looks like. And let's just a brief second, why? What's causing some of this change? And, the world has been moving along quite nicely with a legacy architecture that was really built around the concept of the server. And people built scaled sizes of servers up and they brought servers down. And, the big changes here is in terms of the huge surge in the amount of data that is growing. Where do people put all that data? How do they analyze that data? And the emergence of artificial intelligence and so on to be able to deal with the data. And secondly, there is whether, this sort of a controversial in the press as to whether or not we're at the end of Moore's Law or whether we're at the transformation of Moore's Law, right? But, the notion that the microprocessor alone is going to double in performance every 18 months and provide the needed power is certainly at an end. And rather than being the end of something, it's really become quite liberating when you talk to how the system architects are starting to view this. People are thinking in terms of GPUs, and they're thinking in terms of FPGAs, and they're thinking in terms of custom ASICs. And it's really become an incredibly creative space now, the whole environment of compute. But this environment then says the notion based upon a server becomes limiting. And so people now increasingly want to evolve into a rack scale or cluster scale architecture, as opposed to having a group of servers that just happen to physically be connected together in a rack via a network. They would really like to think of themselves in terms of, I have a group of resources that are inside of a rack, and I want to be able to connect these in just about any fashion that I would like. And quite naturally, rack scale systems start to move then into the conversation around disaggregation. And as Dave and Sumit said, there's a lot of really nice reasons in terms of why people would like this concept of disaggregation. You know, they want to drive better performance. Maybe they just want to go faster. Just simply, they need to go faster. They need more resources. They need to go faster. They highly desire lower latencies and higher bandwidths between elements. They want to precisely tune in the amount of storage and their compute ratios, and so they just need better performance. Or they want to enable better, more capable configurations. That a CPU is perfectly good for some things, general purpose GPUs for others, FPGAs for other things, ASICs for others. They want to combine those elements together. They don't want to be limited by what's inside of a given server. They want to combine those elements together. Sumit did a nice job of talking about converged workloads, right? That you're running a particular job in 1 hour, and you want to reconfigure that system and run a different workload. So there's no particular reason. You've got a rack worth of stuff. They want to be able to do it because the bottom line is they want to get utilization out of these resources, and they want to reduce their costs, both CapEx and OpEx, right? There's really no reason to have 4, 8, 16 GPUs in every single server with an enormous amount of energy consumption if you can get by with quite a bit less than that. But there's one quote that comes to mind here from one of our customers, right? And I put it here on the page, right? That says, there's disaggregation brings lots of wonderful concepts, and we would love to be able to disaggregate, but unless you can re-aggregate those resources back together again without getting killed in performance, you can't do it. And that's really what GigIO brings to the table, is now the ability to put these resources back together again in any sort of arbitrary fashion at performance. So let's talk about this rack scale, because there's been 3 or 4 approaches to doing this, and we'll talk about some of the issues associated with it. So the most obvious answer, and this is one that goes way back, is to simply create a bigger server, right? You want to create a rack scale type system, just put as much stuff as you can possibly shove into a server. NVIDIA, DGX2, HP and others with Superdome servers serving HANA, put memory in, put processors in, put compute in. The advantage here is you really do get good performance, right? These systems really do fly. The downside, they've got these systems completely tuned to the max, and there's a limited ability to scale this system. They're greatly expensive, and generally speaking, the utilization on these systems is not very good. All right, they're great for a particular use, and then you're going to have issues. Approach number 2 to creating a rack scale system is, of course, to try to use your network. Right? It is the network and the legacy architecture that has connected these servers together. So why not just use the network to do it? Use Ethernet, use RDMA over Ethernet, or use InfiniBand. And the upside to doing this is it scales extremely well. Right? NVMe OF shows that you can scale storage systems, as an example, to really quite high levels using servers as the basis of being able to do that. Latency is an issue, though. And latency, particularly beyond storage, is an issue. To be able to connect together compute elements or to be able to connect together ASICs is a problem across a conventional network. There is the complexity of the software and the hardware, and generally speaking, it's proprietary solutions. You can use PCI switching, a conventional PCI switching approach, and really it's a better big server. So you get all the advantages of a big server. You get very nice performance, particularly latency. It will add more elements of compute as opposed to just storage. You get better sharing, right? You can take that resource box, you can move it between multiple servers, you can utilize stuff better, you can share better, and as a result, it's more cost effective. The downsides to this approach is there are fundamental limitations in terms of building scale, and you still need to put together a network so that you can connect the servers together. These new bigger servers, you have to put those together. And so with Fabrics, we believe we combine the best of both of these approaches, right? We completely solve scale, and we give the performance level of the better big server. So we create a network, and I'll use that term as opposed to Fabric, out of PCI Express. We get the performance and latency that people expect out of PCI. It is what runs inside your server, and it is what gives you, 100 nanosecond, 200 nanosecond kind of latency. It works for all kinds of storage and compute. We can scale without limits, right? We scale exactly the same way that NVMe, it is NVMe-OF, so it's exactly the same as NVMe-OF. We can do it for storage, we can do it for compute. We are an open platform. More than one customer has told me, please, please, please do not give me another pane of glass. And as one memorable guy told me, he said, another pane of glass is a pain in my ass. So please interface with my existing management infrastructure. And now, I just run through a real quick an example of this. We can scale up, we can scale out. So at the basis of our system is our switch. You can connect servers to it and run it exactly like that. And we have lots of customers who are doing just exactly this thing, right? They want to put 20 servers on a switch. They want super high latency. They have super low latency, and super high bandwidth, and they want to run TensorFlow or they want to run MPI applications, and they can do this all day long. If they want to add resources, they can take a box. They can take, in this case, a JBox. To us is just a box of flash. There's no compute element in that box at all. It's just a box of flash. You can add it onto the network, and now the servers up above can take advantage of that storage or not. You can also add a storage server. So it could be a storage box with no compute. It could be a storage server where you're running NVMe-OF, and you could have an infinite amount of storage back behind that storage server. So for the first time, whether or not you put a drive directly into a server, you attach a direct attached drive via the network, or whether you put a drive inside of a storage server and use it off of one of your application servers, you get exactly the same performance. So it is network attachment, convenience, sharing, flexibility with direct attached speed. Now what we do with flash drives, we can do with computational elements too. So you can take a box of GPUs, or you could take a GPU server. So you can take a server, it's got a bunch of GPUs in it, you can share it with the application servers that are sitting up above. And in fact, it doesn't really matter. You can put a box of anything. Anything that plugs into a PCI slot will plug into Fabrics. Least of which would be storage class or persistent class memory, because when you think about PCI Express, it is a memory-centric network. And so you can do puts and gets directly across Fabrics. So you can take a block of storage class memory, you can attach it to the Fabric switch, and you can utilize it in all of your servers. We integrate well into all the software environments. You want to run virtual machines, you want to run VMware, you want to run other kinds of virtual machines. If you're a container environment, Docker, Kubernetes, doesn't matter. You just want to run bare metal. And as I say, on the right-hand side, it's all about, our standard Redfish APIs connecting into a whole group of cluster and orchestration software. And with that, I will hand it back to you, Mike.
Thank you much, Alan. That was excellent. Let's go to the panel discussion now, and what we're going to do is we will go ahead and post the audience survey questions, and while they're doing that, we'll actually handle the actual panel discussion. So you should be able to see now on your Zoom screen something that looks like this. Go ahead and answer these questions. We'll give you about 2 minutes to do it. And while we do that, let's go ahead and go to panel question number 1. Oh, by the way, the first audience survey question is, where is your organization in the process of investigating composable infrastructure? And you check one of those answers, please. So panel question number 1 is, how does composable infrastructure today differ from the technologies that preceded it 10 to 15 years ago? We'll start with Western Digital, then go to Liquid, then to Gig.io.
Well, I think kind of at a high level, 10, 15 years ago, you were extremely happy to share a processor, right? You could have a VM and you could stand it up, run your job, stand it down. You also had some virtualized I/O. It lets you share your I/O paths and networking things, but it was not granular. I mean, we were happy with it because previously we had decades of dedicated processors in, single digits of utilization many times that we are now able to exploit and utilize more. But it was really, as you would expect, that long, fairly primitive and not very granular. So that was really where it was 10, 15 years ago. And as myself and my other panelists have shown, we're now hitting a stage where it's much more granular, which practically speaking means you're getting much higher return on your investment.
Excellent. Sumit, do you have any opinion on this one?
Yeah, absolutely. I think mine's along a similar vein. We think, 10, 15 years ago, virtualization was invented to improve the resource utilization of these very expensive CPUs that we were putting into the environment. Fast forward, what we look at ourselves as, just like things like VMware are the hypervisor for the virtualization layer, what companies like Liquid are developing is the physical hypervisor. We do for physical infrastructure what things like VMware do for virtualized environments. And just like VMware was able to raise the utilization rate of that very expensive gear we were deploying into the data center, same thing with composability. We're going to be able to take that even to the next level. Our opinion is that virtualization and composability are actually not in conflict. Hyperconvergence and composability are actually not in conflict. We think the holy grail, or the end point of this whole thing, ends up being when we can start deploying things like HCI on top of CDI, right? When hyperconvergence can be deployed on top of dynamic infrastructure, we think that makes the most amount of sense. When the virtualization layer can reach into the underlying hardware and say, give me another GPU because I have a VDI workload that I need to service. Give me some more storage so I can chop it up for a vSAN environment. We think the marriage of these two technologies will kind of be the best of both worlds.
Excellent. And Alan, what do you guys see from Gig.io? What is your view on this?
Well, I would echo a lot of what Dave and Sumit said, but I would add in, one of the big drivers, and maybe it's just, our company's background. A lot of what used to be in the past were effectively large servers. Big SMP servers, Sun E10Ks. Where people needed to solve some rather large problems and a given server wouldn't do it. And so it was really, a clustering kind of technology. The more exciting 3, 4, 5 years ago, the whole environment towards SDN and FDI software and the movement to wanting to be able to treat it as a composable pool. But, the problem for the SDN and SDI folks is they just really didn't have the underlying hardware that would enable them to play all the tricks that they wanted to. And that's where I think the real magic of where Composable is now starting to catch up and being able to hand the SDN and SDI guys some real capability.
Excellent. And with that, let's go to the next polling question. The second poll question is, what use cases for composable storage is your company interested in? And check all that apply, please. I'm going to launch that poll now. And while that's open, let's go and ask panel question number 2. This one will start with Liquid, then go to Giga, and then go to Western Digital. And that question is, what composable infrastructure use cases have you seen, or use case have you seen the most interest from your customers so far in 2019? So if you could just focus on answering about one specific use case that you've seen a lot, kind of the most compelling one, that'd be great.
Yeah,
we'll start with Sumit with Liquid.
Sure. I think, 60+%, 70% of our use cases in one form or another touch accelerators. And the math is pretty simple. The more expensive the resource, the more sense it makes to share and compose that resource. So without a doubt, our biggest application so far in 2019 has been around AI, ML, DL, those kinds of applications that leverage large quantities of accelerators.
Excellent. Alan, what have you guys seen as the most compelling use case on your side?
Well, I had 2 of them, and Sumit just picked one, so I won't talk about that one because that's an obvious one, I think. The other one that we're seeing, it's really intriguing to us, in the storage world. Storage, I'll call it, generally speaking, storage expansion. And this is coming from both storage system vendors and those organizations that really want to deploy white box kind of hardware and open source software solutions for storage, large scale kind of storage. And now that we do give them this capability of NVMe over Fabric that runs at the same speed as direct attached, there's a lot of experimenting that's going on amongst these system architects to really be able to tune in, I'll call it next generation storage architectures.
Excellent. And what are you seeing at Western Digital, Dave? What is the big thing you guys have seen?
Similar, clearly because of where I come from, it's in the storage space and people wanting to very shared flash storage targets. And it's really been in analytics, a lot of analytics workloads, genomic research, oil and gas, but also a little Wall Street, high-frequency trading, high-frequency transactions that needs ultra-fast storage and access. So that's, and I'm not surprised there because these are markets that have the technical expertise and the resources and finances to sort of be early adopters of this. But so it really is just analytics and a little bit of financial services are really the use cases. Excellent.
I'll go ahead and share the poll results for a second or two, and then we'll go ahead and launch the third poll. The third poll is going to be, what are the greatest concerns that your organization has about utilizing composable infrastructure? And it's to select all that apply. Go ahead and launch that poll. And with that, let's jump to the final panel question. And that panel question is, how do you see composable infrastructure evolving over the next 5 to 10 years? Alan, we'll start with Gig.io, then we'll go to Dave at Western Digital, and then finish up with Sumit at Liquid.
Okay. What we believe is that as the technology continues to evolve, what will happen is that composed rack or cluster. Right? We say the word rack because it's a convenient one, but there's no particular limitation to a given rack. It can be multiples of racks. So this composed rack or cluster, it really becomes the standard building block, if you will, for the rest of the data center. So whereas the server today and yesterday was really the standard building block, and you network servers together, what you will end up doing effectively is you will network these composed racks and clusters together. and it will become the standard building block for AI, scientific computing, big data, for all those kinds of applications that we talked about. This evolves to becoming the standard building block.
Sounds very good. Dave, what do you guys see happening over the next 5 to 10 years?
I'd really have to echo all of what Alan just said, in that it's starting out inside the rack today, in terms of your flash, your disk, your processor, within the rack, or maybe sometimes even within a part of the rack. Moving forward, though, it's going to be the rack might become the unit of the rack might become the HCI of the data center in 10 years. And that you now have rack scale configurability, rack scale granularity, or granularized resources at a rack scale or at a multiple rack scale. So I think I would agree with Alan and with the slide Sumit showed earlier, that eventually it's going to be like VMs are today. You don't know where they are and you don't care. You just have enough resources to meet your application SLAs, and the resources are somewhere, and they're there when you need them, and you're not paying for them when you don't. So I think the scale out aspect will really be the next big frontier to make this kind of technology scalable across an entire data center, and maybe even scalable across geos. So that's kind of where I see it going.
Excellent. And Sumit, what do you guys see it evolving over the next 5 to 10 years?
Great question. Good feedback from all the other panelists here. But I think number one, the move to disaggregation continues, right? So I think we will continue to disaggregate resources as we move forward. New interfaces will emerge that will allow us to start disaggregating things like memory. So we think that trend, absolutely continues. But we think a lot of the innovation is actually going to happen in the software layer. We think the tie-in to higher level orchestrators is going to be extremely important, whether it's Kubernetes, whether it's OpenStack, whether it's Terraform, whether it's Ansible. We're not in a position to say which one wins, but we know that higher level orchestrators are going to play a big part of this entire kind of move towards composability. And we want to embrace that by having the appropriate API and integration, northbound. I think that's one important part of it. Policy-based management will be another part of it. Not only are you going to be able to create your machines the way that you want, but now you're going to be able to set up policies that dictate how that machine operates. When the storage goes above 80% utilized, automatically take this action, right? And the natural extension of policy-based management is AI-based management, where the AI is studying the utilization rate of the hardware inside the data center, and based upon certain algorithms, the AI is now reconfiguring physical underlying infrastructure based upon a best fit model, right? This is our, machine building machine scenario, right? The Skynet example. We think that's going to be an important chapter of how this whole thing plays out. And imagine things like hardware containers, the ability to predefine machine types and have kind of almost a serverless environment where I know what kind of software container I'm looking to run. We, in our environment, have multiple hardware containers that we can best match to these software containers that we're looking to deploy. So we think the evolution of this is really going to be in the software features that we develop on top of disaggregated infrastructure.
Very good. It doesn't look like we have any Q&A at this point. So with that, I guess we can go ahead and wrap up the webinar. Again, thank you, Alan, Sumit, and Dave and your companies for sponsoring the webinar. As I said earlier at the beginning, we'll be sending out the recording and a copy of the slides to all registrants on Thursday, and we'll look forward to the next G2M webinar. Thanks again, everybody.
Thank you, Mike.
Thank you,
Mike.